Let's take a look at the quiz review. I got some feedback from you guys, a little math boo-boo if you caught it. I fixed it, so here what you need to know. The heat equation is Q equals mc delta T. Q is heat, m is mass, c is the heat capacity, and delta T is the change in temperature. And we have a bunch of questions on the back about that. We need to know how to interpret a reaction diagram. Here's our two reaction diagrams. We need to know what enthalpy and entropy is. So enthalpy with the H has to do with heat, and entropy is delta S, has to do with mess or randomness of a system. So that's the definition from our definitions, which you guys should have done. And let's see. Here we have a reaction. It's going uphill. Yes, there's a bump up here. We have our reactants on this side. We have our products on this side. And then in the middle here, we have the activation complex or the activation energy bump. And that's going to be important later when we talk about catalysts. But let's take a look at it's going from the low end up. It's going uphill from reactants to products. Because it's going reactants to products, it's going to be endothermic. You need to put energy in. Don't worry about the hump for now. All you need to know is that's where the activation energy needs to go. And that's the important part is start to finish, not where you get in between. And here we have reactants going to products. It's going downhill. And because it's going downhill from here to here, I made a little arrow. That's exothermic. So energy is coming out. So we're converting our potential energy into kinetic energy or heat energy, which we will talk about in a little bit. And I'll show you a nice little video. Okay, so following the graphs, potential energy. Let's go back. We got the potential energy reactants. Reactants are on this side. Products are on this side. And then where's the activation energy? There it is. And is it exo or endo? It's endo over here. It's exo over here. Okay, so what is exothermic? Exothermic is a reaction that releases heat. So if it releases heat, it's going to get hot. If it's endothermic, it's going to absorb heat and it'll feel cold. What's the activation energy? Activation energy is the energy needed to start the reaction. So we need to get over this hump to get to the product. So it's the energy needed to start the reaction. Just like lighting a candle, you need to light the candle to make the candle burn. You need lighter fluid to start your barbecue. So that's the activation energy to make it go. It just doesn't, your barbecue doesn't just light on fire all by itself. Where does chemical energy come from? It comes from making and breaking the chemical bonds, which was nice in the PowerPoint. Now, the little section coming up here is stuff that's kind of like remnants from level 2, but I threw it in there anyway. If it confuses you, it shouldn't because it's easy stuff anyway. So, energy, where do we get energy from food? Well, that's chemical energy from breaking the bonds of the food molecules that we're eating. Kinetic energy, that's energy of motion. You'll be doing that in physics next year. And then we have potential energy, which is stored energy. Like the Pinocchio guy says, you have potential. So that's stored energy, potential energy. Let's see. We have thermal energy. That's heat energy, which is based on particle motion. So the faster the molecules are moving, the more thermal energy it has, the more heat energy it has, and technically it also has more kinetic energy too. Nuclear energy, that's in the nucleus of the atom. That's a nuclear bomb. Electrical energy is the flow of electrons, which we kind of did in our battery unit. Going electrons flowing, so that's the electrical energy. Conservation of energy means that energy cannot be created or destroyed. So you kind of know that. That's easy. Here's our reactions. Let's take a look at it. We have carbon plus oxygen makes CO2 and energy. Notice where the energy is, or heat, or kilojoules, or whatever it is. It's on this side. It's a product. It's coming out of the reaction. Because it's coming out of the reaction, it is exothermic. Energy out, exo. Okay, and this is barbecuing. And then here we have another reaction. We have water. We put energy in. Look where it is. Energy is a reactant, so you're putting energy into the water. And what it does is it breaks up the water into hydrogen and oxygen, which is pretty cool. Maybe I'll do it for you guys. This would have been a lab, but maybe I'll see if I can rig something up for you guys at home so you guys can see the lab. Okay, and the question is the reaction endothermic or exothermic? Well, the energy is going in, so energy in is endo. So look at the equations. You need to spot the equations. This is exo, this is endo. Just like up here, you need to be able to spot this is endo and this is exo. So that's the stuff that you need to know. Okay. A little bit on entropy. Now, if you guys get confused with the entropy, don't worry. I'm not going to ask you too many questions about them. Thank goodness. So the question is does entropy increase or decrease when air is cooled or liquefied? The answer is it decreases. Why? Because air is a gas, and then it's liquefied, turns to a liquid. So the organization, the mess, and here it is, increase equals mess. This is decreasing, going from a gas to a liquid. So it decreases the mess because it's all coming together in one place. So that is a decrease in entropy. So let's take a look. Here we have two things coming together to make one molecule. Yes, there's a 2 in the front. Yeah. But you got two molecules or two atoms coming together to make one thing. They're coming together. Entropy is decreasing because it's being organized. It's coming together. Okay, here it's breaking apart. You're making a mess. Humpty Dumpty fell off the wall. That's entropy. Okay, so he broke apart. So you're not going to undo the mess. I mean, you can by putting in energy, but that's another story. And crazy glue for poor Humpty Dumpty. So here we have two of the same things, but look, it's changing state. This is a state changing thing. So just like question number 14 up here, we're going from a solid to a gas. And there was a nice video that I think I tried to send it to you, but you guys couldn't see it. I'll send it to you. I'll try to link it to you with this today. It's a really nice video about the entropy of solids, liquids, and gases, which is good. So here we have, that might be helpful for a quiz or question that might show up soon. So here we have a solid going to a gas. So a solid is organized and a gas is completely chaos. So the entropy is making a mess. So it is increasing. So the good news is you can always have your notes with you when you're taking the quiz. Hint, hint, hint. Okay, because it's an open notebook quiz. Then we have so no need to cheat. It's open notebook. So here we have gas to a solid. Open notebook is not cheating, especially when I say it's okay. So we go from a gas to a solid. Now it's going the other way. So we're going from a mess to being organized. So the entropy, the messiness, is decreasing. Okay? So less mess, more mess. So that's the best way to tell is are you making a mess or not. Now this one is an interesting one because this one has two strange things going on. You're dissolving something in water. Doesn't say that, but it's what AQ stands for. So you're dissolving sodium hydroxide to make sodium and hydroxide ions. They're separating apart. So you are now making a mess. And there was a nice little picture in the PowerPoint that showed that that is an increasing of entropy, which is increasing a mess. So a solid is organized, and now it's spreading about, zipping around as ions in solution. Okay, now what about this energy thing? Does that matter? Well, not for the entropy question, but it does matter for the next question. Is it exothermic or endothermic? And look where the energy is. The energy is coming out. So that is exothermic. And this is something that we would have done in school at the end of the marking period, where we would have taken some sodium hydroxide and dissolved it in water, and it gets hot. But wait a minute, we did something very similar to that, where we took a solution, a solid, and put it in water. One got hot, one got cold. So you've seen it already. So that's exothermic, energy coming out. So when you dissolve sodium hydroxide in water, it actually gets hot, which is actually very cool, or very hot, should I say. So here's some calculations. Okay, so if we were in class, and if I'd give you lots of worksheets with these on them, we'd be doing them in class, but they're such a pain on the computer. So here they are. Okay, so we have our word equation. Let's break it up. We have our equation Q equals MC delta T, which I can't believe it. They give it to the AP kids, so I guess you'll get it too. But here it is, Q equals MC delta T. Q, we are looking for Q. M is the mass, C is the heat capacity, delta T is the change in temperature. So let's take a look at our equation and fill in the blanks. So Q, we're looking for how much heat was gained, so that's the unknown. M is the mass is 50 grams. The C is the heat capacity or specific heat, and it says right here, specific heat is given to you as 2.15 calories per gram degree C. Notice I wrote all the units. There's a reason for that. And of course, the temperature is 55 minus 20. And if you can do the math like I couldn't do last night, the answer would be 35 instead of 32 that I did silly math problem. Anyway, so the answer is 35. Hey, if you did the math problem wrong and you set it up, guess what I would do? I'd give you full credit on an open-ended test. But of course, the setup is all that's there. Silly little math problem. Stuff happens to Mr. G too. So, I'm human. Sorry. So, we got Q equals MC delta T. Here's the equation. So let's plug it in. Q equals M, which is the mass. C is the heat capacity. Delta T is the change in temperature, 35. Notice the units. Grams cancel. C's cancel. We're left with calories, which is our unit. So we push the buttons in our calculator. We end up with 376 calories. That is the answer. So that's how much heat was gained. So now we have another similar equation, except here we got the joules. We're given our joules, but we're looking for the find the specific heat. So we're looking for the C. So here's our equation, MC delta T. We do the Q. What's the Q? Q is 200 joules. Not calories, joules. That's okay. Joules is up here. The mass is 15 grams, which it tells us right here. We have the C, which is heat capacity. I don't know. We're looking for that. That's our unknown. And delta T is the change in temperature. 30 minus 15, which is 15 degrees C. So we could plug it in as Q equals MC delta T and solve, but I like to do the algebra with the letters first before moving around all these things. So we want to solve for C, so we take the M and put it on the other side. We take the delta T, bring it to the other side. So we have Q divided by M delta T. So now we plug and play. So Q is 200 joules, because we had that right over there. M is 15 grams, we had it right there. And delta T is 15 degrees C, we had it right there. Isn't it so much easier to do this instead of digging it from the equation? I thought so. So now we have all our things. Look, units don't cancel. What? Oh, that's the units. Joules per grams degrees C. How convenient. And you push the button in the calculator. Bing, bing, bing. We get 0.84 joules per degree C. Or is that a 9? I can't tell. But either case, you're good. Okay, next. We have another one. We have the joules. we have the grams, we have the delta T, we want the specific heat again. So, equation, Q equals mc delta T. Q is 242 joules. Mass of the copper is 82 grams. C is what we're looking for. Delta T is 35 minus 28 is 7 degrees C. So now we have Q equals mc delta T. We want to solve for C. So we take the m and the delta T, flip it over to the other side. So now we have this equation. So now we just plug and play. So 242 joules, 82 grams, 7 degrees C. And then our answer for C, which is the heat capacity or specific heat, is 0.42 joules per grams per degrees C. So that wasn't that hard, was it? Okay, now we have given specific heat. They give us a specific heat. It takes 93 joules of energy to heat a sample of lead from 22 to 40. Find the mass. So now we're solving for M. Welcome to math. Q equals mc delta T. Q is 93 from the equation. M is what we're looking for. C, the heat capacity, is 0.13, given to you, of course. And delta T is 40 minus 22, gives us 18 degrees C. So now here's our equation, Q equals mc delta T. We solve for M. So what we do is we take the C and the delta T, flip it over to the other side, and we end up with M is Q over C delta T. Q is 93. C is 0.313 joules grams degree C. Delta T is 18. The C's cancel, the J's cancel, the G's flip up, so you end up with 39.7 grams. So that was the mass of lead. Easy stuff, guys. So just take a look at it. If you're a little confused with the entropy, I'll give you a nice video in a second with some nice entropy. Hopefully you'll be able to see it. And it's easy stuff. And as usual, I will give you the quiz review followed by the quiz. Make sure you do the quiz review first before you take the quiz. And the quiz review will look just like the quiz questions. They'll be a little different, but they will look very similar. So do well on the quiz, do well on the quiz review, and if you have any questions, feel free to email me. Toodles! Happy Wednesday. What? Wednesday?